Yeah, he's going to be here in a little bit, but he told me we should start. So welcome back everyone. This is session 5, I guess, for the summer study course, so we're halfway there. And today we have Anupam talking about quantum control and its relation to the groups.
Thank you, Pablo. So as advertised, I'll talk about introduction to quantum control. And I use the word introduction because we barely scratch the surface and we'll only talk about some aspects of it. And we'll mostly look at things that are related to what we've been studying about, especially the idea of Lie groups and Lie algebras. And in a lighter way, we want our quantum systems to do what we want. So I want my H bars, as Ivan once said, H bar to the people. So with that, let's get started and talk about quantum control. So typically, quantum control is, we want to ask for a particular experiment. By the way, is this legible? Is the font size okay? Awesome, thank you. So for a particular experiment described by some dynamical equation. Now the dynamical equation could be the time-dependent Schrodinger equation or the master equation, depending on whether you have a closed quantum system or an open quantum system. So I write TDSE. I guess we all know this is the time-dependent Schrodinger equation or master equation. So can we affect or can we cause, let's put it this way, and cause and we bring about a particular quantum mechanical process? And this is very vague and some examples will be clear as we go on. So this is the question that we'll try to look at to some extent. So we are interested with, for a particular given experiment, given by a particular dynamical equation, can we cause a particular quantum process? And by cause, I mean affect it in some way of our own. So from a perspective of QIP, so for quantum information processing, which is what most of us are into, so we are interested in a few. I'll give you a few examples of what the kind of task we are interested in. So firstly, we might be interested in quantum state engineering, and let's look at some examples of that. So I could be interested in preparing a particular state. So we call that, I'll call that a state preparation. So what I mean by that is, given, or let me write this way, drive a known initial state to a known final state. This is the simplest example that we think of, and we'll look at some examples of this. We could also have state stabilization, which is typically involves taking a lot of states and bringing them all to one state. So we want to drive an unknown this time. We do not know what the state is, and arbitrary initial state to a known final state. Right. So typically, an example of this would be some of the things we've read about, where people try to prepare highly entangled states like Schrodinger cat states. This would be an example of having a dissipative environment where we want the steady state to be a particular state, often which has used for methodological reasons. Another example would be of this is state purification, and an example of this would be laser cooling or preparing a pure state. So we want to drive a mixed state to a pure state. And of course, I could mean any pure state, I could mean a particular pure state. So these are the kind of tasks we are interested in. Another thing which we want to do is quantum process engineering. So here we could be interested in preparing gates. So let's call this unitary gate. So I want to implement a gate. For example, if you want to build a quantum computer with fault tolerance, we want to implement a set of gates that are universal, like the Clifford gates, and one non-Clifford gate, like the T gate. Alternatively, we want 1 qubit rotations or 2 qubit tandem gate. For some applications, we might also be interested in implementing a Krauss map. In fact, one example of a Krauss map that we want to implement is something which purifies a particular state to a particular mixed state to a particular pure state. And we also might want to synthesize generators. So this would be an example of this would be generator synthesis. Would be when we want to do quantum simulation. So this is something which our colleagues in Arizona are trying to do to some extent. And finally, there's one last category I'll talk about, that is fighting decoherence. And most of this goes under the topic of dynamical decoupling, which we just heard about in the archive. So we want to dynamically decouple a system from the environment so that decoherence is minimized. So these are some of the things. This is not exhaustive, but for today we'll focus mostly on this unitary gate synthesis and state preparation, because these go well into the idea of some of the Lie groups that we have been talking about. So there are some aspects of these problems that I just want to bring to your attention and focus on some parts of it. So there. Yes.
Sorry, could you just remind me again what's the difference between the state prep and state stabilization?
Like state prep means I have a particular initial state, I want to drive it to a particular final state.
Okay.
For example, given a product state, the 0, 0 state, I want to prepare a Bell state.
Okay.
State stabilization means I want to drive my system to a particular steady state. No matter what my initial state is, I want to drive it to the same state. This is often done in the case of stabilizing a state of a dissipative system, right? So there are 3 aspects to a quantum control problem. So there are 3 of them, and I'll just list them out, but we won't talk about all of them. So the first aspect deals with controllability.
Anupam, there is a question back here.
Yes.
So what is, I mean, it is probably extraneous, but what is the point of state stabilization if you are using arbitrary states? I mean, if you are using arbitrary states anyway, can't we just simply take a known state and get
So the thing is, oftentimes when I prepare an experiment, the initial state is not fixed. It could be a mixed state, it's usually a thermal state, and I want to stabilize it to a particular state that I want for my task, which might have some useful for metrological application, for example.
This is like cooling, right?
Well, yeah, cooling is one example of that.
Okay. So is
I mean, I would also point out these are not mutually exclusive. I'm just giving you a flavor. This is not exhaustive or mutually exclusive. So these are the kind of problems you want to look at, and I will focus only on these 2 for today.
Right. I mean, really, the others aren't really related to Lie groups, right? I mean, they're
Yes.
semi-groups, and it's a big problem with whether
Right.
you could
Yeah.
make that work anyway.
Yeah, so thank you, Ivan. I'll point out the others are related to semi-groups and not related to Lie groups, so we won't talk about them. But since we want to talk about quantum control, I thought I'd give you a flavor of the other ideas. So for any problem, including those that involve semi-groups, there are 3 aspects. One is controllability, then there is control synthesis, and then finally there is a notion of optimization. So let me explain what these things mean. So controllability asks the question, can we achieve the objective, or let's just call it our objective? And again, the objective for this is, for the purpose of this conversation, is the process, quantum mechanical process we want to implement. So can we prepare the state that we want? Can we prepare the unitary gate that we want? We could also talk about these, but they involve semi-groups. Control synthesis is asking what properties of the system and controller achieve the objective. So, assuming that I can do this, how do I know that I have reached my target state or not? Or if I want to do spin squeezing, how do I know I have got the maximum amount of squeezing that I could have got? And finally, optimization is about how do we get there, or how do we achieve this, given, of course, some constraints that model our experimental system, some penalties. For example, we may not want to, we might have some forbidden state that we don't want to get into, etc. So, what we'll talk about mostly is the idea of controllability, and it has a lot to do with Lie algebras and Lie groups, because the dynamics of pure quantum states is related to some of the Lie groups. So we will talk primarily about this. We will not talk about control synthesis, although if you want, we can talk about this offline or otherwise. It'll also be clear when we talk about representation theory later, what some of these objectives can be. And we will not talk at all about optimization. If you want to learn, Pablo is the expert on that, so one can go talk to him. So I just want to talk about controllability. So are there any questions so far? Okay, great. So now we want to understand what does it mean for a quantum system to be controllable. So before we get into that, let's think of a general dynamical system, which is governed by some differential equation, and ask ourselves, what are the possible states it can reach when it is evolving under that dynamical equation, which is typically a first order differential equation in time. So, in order to do that, we have this notion of something called a reachable set. So first let's consider a dynamical equation. So let's say I have d dt of g of t, where g is a group element. And let me write this down, and I'll explain these terms one by one.
By the way, are you following any particular reference, or are there a set of references?
There are a set of references.
Okay.
I'll have them in the notes when
Okay.
I make them available.
Terrific, thank you.
So what I have is the state of a system given by this variable g, which, slightly jumping ahead, is a group element of some Lie group. That's why I have used a suggestive notation g, which we've been using so far. And I have these generators, if you will, A0 and AK, which in general may depend on the group element I'm at. And I have these controls. So these are the controls that I can apply to the system in order to affect a dynamics. Now the question is, given the set of all controls, so let's say my controls, and I'm going to use C to mean the set C1 through C capital K. I have capital K of them and I index them by lowercase k, if you can distinguish them. So given this, what, and of course this, and initial condition that G0 is the identity. Now if this seems too vague, you can think of this as, in the context of a Schrodinger equation, the propagator at time t equal to 0 is the identity, right? This is talking more familiar terms. So given the fact that initially I am the identity element of the group, what is the set of group elements that are accessible? one thing which I didn't explain, or I should be a little more careful saying, is here I have chosen a particular set of values of these controls. In general, they can belong to a set of parameters that I can use from a control, and I'm going to call it K. If you speak LaTeX, that's \math K. Yes?
Is the thing on the right hand side of the equation meant to be like Hamiltonians?
Yes.
I'm thinking
So,
the thing on the left hand side looks like a Hamiltonian times a unitary.
so if you want to think of this in terms of quantum mechanics, think of this as a time-dependent Schrodinger equation.
Right. So the thing on the right hand side actually has unitaries on the right hand side of the equation.
Yeah, so that's a function, right?
Okay.
In this case, it's a linear function. But in general, it may not be a linear function. So yeah, this is really this times this. So I'm multiplying the group element by the generator. Yes. Right? So this is the question which I want to ask. And to answer this question, we define a concept of the reachable set. So let's call this the reachable set R. This is the script R. To speak LaTeX, it's \mathcal R. Not to be confused with math BB, which is the real number. So this is the set up to time t. Notice that the independent variable is time. Is this, and I denote that with R less than equal to t. This is just a union, or let me call this capital T, of all things I can reach up to this time. Now this sounds like a recursive definition, but I start with the base case that at t equal to 0 or r equals 0 is just the identity element of the group, or if you prefer the quantum mechanical language, is the identity on the Hilbert space of interest. So this is the thing, this is defined as the reachable set. Then we define the transitive reachable set. Yes.
I mean, well, maybe I should if you want, but I mean, that first definition, as you said, it seems kind of recursive, right?
It is, but this is the basics. So then, I mean, this is not a constructive explanation, this is the definition. So I'm not telling you how do you find the reachable set, I'm just telling you this is the properties it has. So at t equal to 0, I can only be an identity. But then I say at some point, how far can I get?
Okay, but you could also get rid of that thing by just saying, well, you can define the reachable set at time t, small t. Right?
Sure.
And that's just the set of all group elements that can be reached from identity by some choice of them.
Sure. Well,
No, you don't have to do that. I'm just saying, you know, that is correct, right?
yes, that's equivalent.
And then you do the union of all of this
Yes,
from 0 to small t. And
Yes.
that's what you have on
That's
the
right.
right hand.
thank you. So I could alternatively say this, let me write it down here. So let me write it this way. Thank you, Pablo. This is the set of all little g's belonging to the group where I do. So this is my group. Reachable up to till time t with some choice of C, the set of controls belongs to the set of admissible controls, right? So then if you look at the transitive set for this, which is simply just take the limit that capital T goes to infinity of R of T, or equivalently I could just take the union of capital T, all possible values of capital T, and I'm going to call this R, right? And this is what we'll primarily be interested in. So, you know, if you speak the language of speed limits, then this is how far I can get in time t, and this is how far I can get at any time. And typically, since we are talking primarily about controllability and not talking about finite time controllability, and we are not talking about synthesis and optimization, we will only talk about reachability or the transitive reachable set, right? So from now on, I'll just talk about what this is, right? If you are interested in how do we do this quickly, we might be interested in this, but I won't talk about that, right?
Do we know, or do you know, the royal view? If I have a fixed final time, I mean, are there cases where I can reach the whole group in a finite time, capital T? Or cases where I can't, where I need an infinite amount of time?
There are indeed some cases of that. So one example of this would be, and I think Pablo can help me out here, is if you have a group that's not compact, then you need infinite time. If you have a compact group, then you can approximate any group element to arbitrary precision in finite time, but you cannot reach it exactly. There would be a set of measure 0 in the group that you cannot reach in finite time.
And there is also, there's also here a distinction between the set of admissible control and the fact, suppose you don't have this A0 term in the equation. So in that case, that system is called homogeneous because basically you have a control field with every term in the equation. So in that case, it doesn't matter if it's compact or not. You can reach any element of the group in a finite time. And if the set of, and at the time only depends on the set of admissible controls that you have. If that set is unrestricted, then you can also generate any element in an arbitrarily a small time. Now, if you do have that term, or say more generally, if the system is not homogeneous, then it becomes more complex.
Yes. There's one more thing I want to point out, that right now I'm only talking about what the reachable set is, and I haven't, as so far, defined what would that be for it to be the whole group of interest. So typically what you would have, I'll write this here, sorry, man again, is that the reachable set is a subgroup of the set of the group G in general. And if this is equal, then we are controllable in some sense of the word controllable. If not, we are not. So I'm not defining that yet. We'll get there. So I just want to point. Yeah.
Sorry, one other question. Your C1 through CK, are those necessarily fixed and they just have some pre-parameter like time? Or is it that like I can actually choose what that function is?
You can choose what that function is.
Okay.
In fact, the point about reachable set is for any function you can reach there. Or said another way, it's better defined as there exists a choice of these functions that will get you to that particular group element in some time, finite or otherwise. Right? Thank you. So just before I did kind of say this is a subgroup, but let me explain that. So if I have a control C1 implements the group element G1, and by implements I mean as a solution to this equation here, it gives me G1 at some time, and control C2 implements G2, then I can put these together and concatenate and let me write concatenation like this. C1 and C2 gives me the group element G2, G1. And I've written it this way to be very suggestive of matrix multiplication, which we do from right to left. Right? So there is a group property. Now I'm sweeping under the rug why this is a group, but just to give you a flavor of why this behaves like a group. Correct? Are there any questions so far?
So I don't have the time at which I reach G1 doesn't have to be the same time that I reach G2.
It doesn't mean. So I could
T1
say
and sometimes
at
T2.
T1, at T2, at T1 plus T2. And another point I'd like to make is this may not be the best way to get to G1, G2, G1, G2. It's just a way. There could be a better way, right? So most of these states are existential.
I just want to make a comment. So, of course, we only define what a reachable set is, right? But the reachable set is, of course, a set of the whole group. It might not be the whole group.
Yes.
Right? So that's the issue of controllability which we have just mentioned, but we can't define.
Yes.
So I just want to point out this property, right? So if you remember, the group property is that one, and it's also the existence of an inverse.
Yes.
Right? So this set might not have the inverse of G1 for all, right? For
Yes.
every G1 in the reachable set, the inverse might not be in the reachable set. It would
That's
only
right.
be so if the system is fully controlled.
That's
which
right.
talked
Yes.
about.
Thank you.
So the existence of the group or that property does not make the reachable set a group.
Yes,
It makes
thank
it
you.
a
Yes.
semi-group,
Yes.
which is a
It is a
less
semi-group.
restrictive condition.
Yes.
So the reachable set is always a semi-group, and it will be a group when the system is controlled, as we'll see in a bit.
Yes. Thank you.
Is there also some terminology that describes the case when you only generate a subgroup?
I think, I'm not sure if there's a standard terminology for that, but typically what this means is you can generate a subalgebra and you're controllable in that subgroup. I don't know if there's a specific terminology for that.
I don't either, but it does happen all the time.
It does. In fact,
and
Yeah.
one of the examples that you're probably going to give.
yes, I have an
Happens all the
example
time.
where that will be the case and we'll get there, right? So now that I've given you a flavor, maybe a good one, maybe a bad one of what we are thinking,
I'm
the
hungry.
reasoning about, I just want to talk about some notions of controllability and quickly tell you what they are. So I could have complete control, so notions of controllability. So firstly, I could have complete controllability. And in some sense, while we were reasoning about everything here, we were assuming that was the case, but it need not always be the case. So what this means is the reachable set equals the group. In the language of quantum mechanics, the reachable set is the group UN, where this is the dimension of the state space. Now, some of you might be debating whether this will be U or SU. We'll get to that in a minute.
So most of the data is infinitely okay.
On N.
Yeah.
Well, it is controllable. It would, so if this can be true, then it's controllable, right? I'm not saying whether the system is controllable or not. I'm just saying if this is true, then it's controllable. If I can somehow show that it's controllable, that this is true, I can show it's controllable. But typically for infinity, I usually can't do it. And second, I have operator controllability. Or this is also called density matrix controllability. And the most familiar thing which we are used to, unitary controllability. What this really means, and I won't write in terms of R and G, is that, and let me now use the language of quantum mechanics. Given a matrix M0 and M1, which have the same spectrum, right? And sometimes this is called kinematically equivalent. So you can think of this as two density matrices, for example. You could also think of them as different components of angular momentum because they have the same spectrum. I can find U belonging to G such that U M0 U dagger equals M1, right? For all M0 and M1, right? So what this means is I can take any matrix with a particular spectrum and find a group element that can do a similarity transformation on it to make it into any other group element with, any other matrix with the same spectrum, right? As it turns out, this is called density matrix controllable because if these were density matrices, then this would be the case, that if you start with a density matrix of a particular rank, you will get, and you can make any other density matrix of the same rank and the same step, same level of mixedness, if you will, or same pure. And also, if you think in the Heisenberg's picture of quantum mechanics, what this means is I can take any operator and transform it to any other operator with the same spectrum. So another example could be I could take Jz to Jx, for example, or let's just call this J about some axis n up to J about some axis n prime, right? This is the Heisenberg picture. And finally, in the Schrodinger picture, so this is the Heisenberg picture, and if I talk about the Schrodinger picture, I can think of, I can map the identity, starting with the identity, I can go to any element U belonging to the group SUN. And this is often the canonical paradigm of quantum control that we think about. So here I don't care about the overall phase because most of the things I'm interested in involve a U and a U dagger, so the overall phase goes away. So the idea is I can map the identity to any element in SUN. So this is operator controllability, density matrix controllability, or unitary controllability. Are you okay so far? Great. There are two more notions that I want to explain. Mention.
Whether I go to an element within SUN or UN would depend on the Hamiltonian.
It would,
right?
absolutely.
I mean, so I can't I have unitary controllability on UN? I don't have to restrict myself to SUN. If
yeah.
I care to do so. I mean, at the end of the day, the overall phase may not matter, but I might be able to do that if I wanted to.
If you want to be, it should be. Yes.
Okay, I'm for that.
I have modded out the U1 overall phase. But said another way, I can always set my Hamiltonian to have trace 0. And then I can make this claim.
I'm sure.
To-
But in that case, is there a difference between complete controllability and unitary? I mean, when you say unitary, you're just talking about quantum mechanics.
Yeah, I mean, this is really what we are mostly interested in, but people usually mean this when they say complete
And these
control.
are not these.
This is too form. In fact, we really care about this case too, right? So there is a third one, which is something which you're often interested in, which is called pure state controllability. And what this means is just I can take any pure state to any pure state, right? So I can, so there exists U belonging to the group G, or the reachable set, sorry, such that I can take a state psi, apply unitary U to it, and get the state phi. Now, if you want to be very careful, I should actually say this. There's an overall additional phase here. This is the question of SU versus SUN versus UN. But they are equivalent as far as we are concerned, because in physics we really care about what the state is and we don't really care about the overall phase, right? So the point is I can map, so yeah, point out for all psi and phi belonging to the state space in question, right? This is oftentimes what we are interested in. And there's one final one which I just mentioned, but I have not seen this being used much. It's called observable controllability. And basically the idea is I just want to map some moment of an observable to something else that is kinematically equivalent to it. So what this means is, so let's say A is an observable. There exists U belonging to the reachable set such that excuse me, a trace of U dagger rho, sorry. is the initial state. Such that these two guys are kinematically equivalent. And I know this sounds heavy, but the basic idea is I can convert it's like just mapping a density matrix to another density matrix with the same spectrum. In the same way, I have the trace of the product of these two should be conserved, and I should be able to make any such unitary which does that, right? So, are there any questions?
Yes, I understand.
I don't have.
I thought that typically with my recollection, which is poor, serves me, is really, it's slightly different than what you wrote it down. That really the idea is that what I want is a target expectation value.
That is a subset of this.
Yeah, but that's, no, I think that this is very restrictive, right? I mean, when I say I have a desired target expectation value, which is on the left.
I mean, that equality is always true because the identity is always on the origin of the set, and that statement is true if you use the identity.
That's right. In fact, what you were talking about expectation values would be true if I choose specific operators. But when I say it's any observable, then this actually ends up being equivalent to this, because I can write the density matrix as a, in a basis of observables.
Very odd thing to find.
Yes.
I mean, typically, what I has understood the point of this, before is that I don't care about the whole state, but I want to make a particular expectation value. And can I?
You're right, and that would be, I think there's a name for it, Pablo, maybe you remind me of that, quantum steering or something.
No,
But there is a name where you just want specific expectation values. That would be a subset of this. Or maybe I should call this full observable controllability. And what you are talking about, Ivan, is observable controllability for some of them. Full observable controllability is equivalent to this. So in our language, we want that R should be SU in this case, for full.
This definition says that the expectation value is conserved in time. So if at time equals 0, expectation value is something, at a later time it will be the same thing. And I don't think that's typically what I want to do. I want to reach, it doesn't really matter.
I think
I just
we have to look into that.
Yeah.
I think that what goes on the right is not going to something. Okay. You just put some other state on the right, then that's fine.
That's what I think. Yeah, that's what I would guess.
Because that what you have on the right is a set of all possible expectation values of it.
I should probably, yeah, you're right. So that's what I mean by kinematically equivalent.
Right.
So I should
That
probably.
shouldn't be row 0. That should be row final.
Exactly.
Then I would.
This is what I mean. So I can get all of these that are kinematically equivalent to this. So all rows for which this is kinematically possible, like the spectrum is such that this is true. So I should, this is not really equal to. Okay, I'm being a little sloppy here, I just wanted to get this out of the way. But I'll mostly talk about pure state controllability and unitary controllability.
Okay.
Alright, so.
Sorry, I just one other question on that point. I mean, if what's the case that we're trying to make some other expectation value? Is this not just the same thing as density matrix controllability?
It is.
It is, okay. There you go.
Unless, so if you want it true for all possible operators, it is the equivalent. But if you want a subset, that would just mean fixing some components of the density matrix and not all. It would be a subset. So I guess that's why I should make a distinction between full observable controllability versus just some subset of observable controllability. Now, unfortunately, in the literature, they don't make this distinction, and they say that these two are equivalent.
That's why I think that should be row sub 1 on the right-hand side in the same way.
Okay, so
Then if you look at your definition on the left about density matrix controllability, then it makes sense, right? Because on your left there, you have behind you have row 1.
yes,
And then they're an exact equal. And then if for all A, then they're equivalent. But
Yes.
for a subset of A,
right.
then it makes sense.
So I guess I'll explain this.
Yeah.
So if I have a density that is kinematically equivalent, and by that I mean there's the same spectrum,
Yeah.
I can do this for all operators, for all observables.
And it's a more restrictive case if it's less observed.
Yes, if it's less than the rank of the Lie algebra. But we'll get there.
Yeah.
Thank you. Right. So let's just jump into pure state control, and I guess I'll give you one example of it, and there are two ways, and probably I'll state the other one and not get into a lot of detail about it. So for pure state control, as we have over here, I want an initial state and I want to map it to a final state. And the claim is if the reachable set is SUN, then we have pure state controllability. But while I explain this, I want to say a couple of things. Notice that this is not true. It's not the other way around. Pure state controllability does not mean I can do SUN, but this is a much stronger criterion. In fact, this is unitary controllability. So what this means is if I can make any unitary, I can make any state, but not the other way around, right? Another thing, I'm going to switch notations a bit and use the term L to call the dynamical Lie algebra. Of the Schrodinger equation. So in this case we have I D E U in H. Right? So you could think of this as the new definition of what we call R. Right? So, and I'm doing this because we are talking about a Lie algebra and we want to talk about generating groups and subgroups. Right. So
You mean the output of the group? Oh, the algebra of that. Okay.
yes.
Yeah, sorry.
Yeah, that,
Right. So I should probably be more careful. You could think of this.
Gotcha. All right.
Yeah. Yeah. The exponential map of that is this. Right? But I will use this term. I won't use R now. I just use e to the R. So think of taking a logarithm of the radian. So now another terminology is what's called a transitive Lie group. And this is just a notion of terminology. It's just something which we know. So a Lie group, it's sometimes called a Lie transformation group, but I'll just call it Lie group. G is transitive on a manifold N if for every P and Q, which are points in M, so these are points, there exists a G belonging to the group which takes P to Q, right? So, I mean, this is kind of, I mean, if you are feeling very smart today, you probably figured that this is the kind of thing I want to show, where the manifold is a set of all quantum states and P and Q are two different states. And if I show that my Lie group is transitive, then I have pure state controllability, right? Great. So now, in particular, that's exactly what I'm going to write down. For the case of quantum control, the manifold is the state space of all quantum states in the pure states, because we are talking about pure states only. And the group is the group SUN, but we haven't proven controllability yet. Although I guess I did see the result in the beginning. So so the thing which we are interested in is that the manifold is Sn-1 complex. So this is the complex sphere with radius 1. in n dimensions. And my quantum states, let's say psi, my initial state, and phi belong to this. So I'm also required that the states are normalized. So I guess it's clear that pure state controllability is the same as saying that this is transitive on this manifold.
Hello?
Yes.
I think we have a question.
Yeah.
And I have a comment.
Yeah, I was gonna say, is this exactly the same thing as this complex projective space?
This one?
Yeah. Yeah, I'm just wondering, like, are different points on the sphere necessarily identified with each other?
Well,
Or is this like, I don't know. Yeah, I mean, yeah.
so what I'm thinking about is just the sphere itself. I mean, of course, this is what you get after you do the projection. And I'm thinking of the class of points. You know, I'm taking one particular equivalence class of points which are normalized.
Yeah.
So I don't have, I don't.
Okay.
Given a
Yeah,
state, I don't
guess the
have a
normalization
larger version of it.
existence. Yeah. Okay.
No, yes, I was just wondering if you want to find what the dynamic will be algebraic. Are we going to do it?
Yes, thank you. I am going to do that. So, going back to our equation here, let me write it again. So, I'll write down the Hamiltonian completely again. Well, these guys put the principal will be functions of time. So, the dynamical Lie algebra is the span of these matrices that you see here. And what this means in the notation that we talked about earlier is the basis of these and linear combinations and commutators there also in high algebra. So what I mean by that is all of these matrices, the linear combinations and their commutators, that set is a dynamical Lie algebra. So I'm going to call this script L. Right. Any questions? Right. So, and another way of saying this is there exists U belonging to the L such that phi is U psi. Right? This is what we want to show. Okay. So before I do that, I just want to define another idea, the idea of a stabilizer. So we want to talk about the stabilizer group of a state, and this is related to the idea of stabilizer that we often talk about in the context of quantum error correction. So,
Just a quick question before you do that, 'cause I have a quick question.
yeah.
So we were saying that generally speaking, the reachable set is not a group,
Yes.
it's a semi-group, unless it's fully controllable.
Yes.
But this thing is always a group.
It's an algebra.
No, but if I'm to exponentiate it,
Yes.
a Lie group, the e to the L is a group.
Oh yes, it is.
But it's not always
Yes.
the whole group,
Yeah.
which means it must be a
Sub-
subgroup. So that means that,
But
but
there is one technicality thing,
okay,
which is what you said is correct.
Okay.
It's an excellent point. But there is something that Anupam wrote which was kind of not generally true, which was
Okay.
that R is equal to X mapped out L. So that the ritual set is the exponential map on the dynamical graph. That's not always true.
it's all, so is that
Yeah,
clear
yeah,
what I
yeah,
said?
yeah, I'd like to clarify that, because I
So
think,
this statement, so what I said was that, you know, we wrote this, right? We said that this wasn't a group, but this is a group, right? So there is,
so there's a problem.
yes. And the
Unless-
problem
unless
is
we're-
that this equality is not true in general. And so the technicality here is that this is true. This is true. If this is compact, which we haven't talked about much. Tyler's going to talk about that.
Lucky you.
And so the idea there is that, so when we're talking about matrix Lie groups, at least I think of compactness just as boundaries, right? I mean, for example, we're talking about matrices which, you know, belong to the corresponding group and they are also bounded. For example, the special linear group, let's say, I don't know, 2R, right? These are 2 by 2 matrices with determinant equal to 1. These are not bounded matrices, right? Not necessarily, I mean. But the special unitary group, these matrices are bounded. The elements of them are bounded. So this is non-compact and this is compact. So when E to the L is compact, when this group is compact, then this statement is true. This is a group, and then we're all happy.
And it doesn't have to be the whole.
It doesn't have to be a whole group. It
subgroup.
could be a subgroup, yes.
Right.
We're not talking about
Yeah, but
full
E to the
control.
L is always
a group.
a group,
Yes.
and it's always a subgroup of the whole group, but it might not be equal to the reachable set.
Exactly.
Okay.
So when things are not, so the fact that these can break down when the group is not compact makes everything much harder because it's harder to characterize this, right? So
Yeah.
this picture that holds always for compact groups, it can also hold for non-compact groups in certain cases, but we cannot prove that. But for compact groups, this holds all the time, makes the whole analysis simpler. And in particular, it applies to a unitary group, which is the one that Anupam was talking about. But you can come up, if we have time, we can do it. We can come up with an easy example of a system, like a control, system like this, but without the eyes, right? So in a general matrix Lie group, that in which it seems like this V alterates the whole thing, but the system is not controllable, and that's because this equality does not make any sense.
Hmm.
But if we can talk about that afterwards.
So I guess I should say that most of what I'm talking about works with finite dimensional Hilbert spaces where things are compact and we're talking about groups like this. Thank you. So coming back, so in order to show that, show that this when under what circumstances is true, I'm going to define the idea of a stabilized group. Or it's also called the isotropy group. And again, we define it in terms of a manifold and a group. So consider consider a manifold. Say there's a manifold M, and we have a Lie group G. Oh, and this is connected. This is connected manifold M. And Lie group G, and say P is a point in M. So the set of elements G belonging to the group which leave P fixed is the isotropy group or the stabilizer group. So in the language of quantum mechanics, the set of operators S for a state has diffeomorphism. And just to remind ourselves, this is just a differential isomorphism. From the quotient of G divided by G to the manifold itself, right? So you could think of this as the set of states, and this is the set of all elements modulo the stabilizers, right? And you can see where I'm going from here, because these are the set of things that will change the state, and these are the states themselves, right? So, of course, this is smooth and differentiable and all of that. So with that, let me just show that the special unitary group gives you is transitive on the set of quantum states in n dimensions. So the statement which I had erased because I was not thinking, or as I would say, I'm a bad professor, or I will be a bad professor. So I will be. I'm not one yet. So the statement I want to show is SUN is transitive on Sn minus 1c. Right? This is a manifold, this is a group. Or this is what I mean. SUN implies, so in other words, SUN implies pure state controllability. I hope you can see the SUN is that. Right. So now clearly, as we know that this is just the exponential map on the Lie algebra SUN. I hope that's legible. My version of math crack SUN, which are just a set of n by n Hermitian, anti-Hermitian matrices in zero place, which has a dimension n square, and dimension of SUN is n squared minus 1. So now, let's say I want to map a state psi to the state phi. And what I'll show is that this can be done with a unitary matrix, which is quite straightforward, but we'll just do it. So consider a matrix U, which is defined as follows. Right? It's not unitary yet, but as you can see, this does the job. Plus and some phase relationship. Now, this clearly does the job. And if I make the set of phi j's to be orthonormal, and also psi j's to be orthonormal, right, where j goes from 2 through n, then I can see that this gives me u dagger equals u, right? Therefore, was that? Yes. Thank you.
You mean you that
This is what I mean, right? So yay, the u belongs to un, which is, so this is the matrix, this is the group. And then of course, I can divide or multiply by some phase factor such that determinant of u equals 1. And then I can say that this u to be in SUN, right? So this is like a very roundabout way of saying something which most of us intuitively knew already, that if you have the group SUN is transitive on the manifold of quantum states in n dimensions. So another way, if my dynamical Lie algebra is SUN, then I have pure state controllability. This is a very complicated way of saying that. But this one thing which I want to bring up is if we look at the stabilizer group, of say what we mentioned state psi, right? In order to do that, let's go to the representation such that psi is represented by the column vector, which is 1 in the first point and 0 everywhere else. Right? I can always change to the basis where psi is this matrix. And if I do that, any matrix which is this form, let's call this x bar, x1, 0, 0, and this is y. So these are not Pauli matrices, they're just elements of group. Sorry, this is n by n. This is n minus 1 by n minus 1. As you can see, this clearly is a excuse me, stabilizer of the state psi, right? Because now if I do x psi, I get psi, right? Now, and of course, y itself is an element, and assume that I mod out, have a way of getting rid of the overall phase. So y is an element of SUN, right? So now let's just talk about how the parameter space of the group space here. So now let's talk about the space of this group SUN.
Is y not an element of SUN minus 1?
Yes,
Minus
sorry,
1 by
sorry.
n?
Thank you. Right. Thank you. Right? So what I want to do is do this G over GP, which in this case would be SUN over SUN minus 1. And this should have a diffeomorphism to the manifold itself. Right? And just to see that, the number, so this should be isomorphic to the set of all quantum states. So this is the sphere, the complex sphere in n minus 1 dimensions. Right? So let's just do some parameter counting to convince ourselves this is true. So the dimensions of this the left side is just n square minus 1, that's for this guy, minus n minus 1 whole square minus 1, which if you do it up, work it out, is 2n minus 1. And the dimension of this is also what we want it to be. So that's a good sanity check to show that this is indeed true. And also right? So I guess what we have shown is a very roundabout way of seeing that if you have SUN is your dynamical Lie algebra, you have pure state controllability. Now it turns out that there's another way to show pure state controllability, and I will not elaborate that in a lot of detail, but I'll just write the result and then talk a little bit about unitary controllability. But how much time do I have? 20 minutes, okay. Hmm?
15.
Okay, thank you. So, another way to show this is if the dynamical Lie algebra, and you could think of this as this because we have a compact group. If this is conjugate to the compact symplectic group in n dimensions, that also implies pure state controllability. But I will not prove this. Yes, I will define that. But these will be there in the notes that we'll put up, so you can read that there. And the compact symplectic group in dimension is the intersection of SUN with the symplectic matrices in n dimensions over the complex field. So it's just a set of n by n symplectic matrices that are also special unitary. Right? So now we want to, are there any questions?
Why do I care about
Why do I care about that? Well, typically I just showed you what it means to be controllable, and in some problems it's easier to show this is true
Okay.
than to show full SU1 controllability. And this is especially true if you have groups that are not compact, then you want to say I can prepare specific states, but I may not be able to make any unitary. Especially if you want to work with harmonic oscillator states, these are the kind of things that you want to think about in that context. Right? Now, I haven't talked about full controllability, but you just have to add, an overall trace term to both this, and SUN in order to get that. So I probably will not get into that. So let's just talk a little bit about unitary controllability. So for unitary controllability, so when we talked about pure state controllability, I said I'm going to take a state psi to a state phi. And I don't care about what happens if I start in a different state. But if I want to do a unitary, I want to do this for psi 1 and phi 1. I also want to do this for take psi 2 to phi 2, all the way up to psi n to phi n. Not only that, I also want a specific phase relationship between these things. So I could write down a unitary that I want to implement. Let me call that W to be some phase followed by a map from the state psi j to phi j. So I want to map the state psi j to phi j with a particular phase, and I want this phase to be definite in order to make the full unitary matrix.
So why couldn't I define, I mean, every state has a phase convention.
Yes.
So why couldn't I absorb those 55s into my definition of the state? I mean, I can call.
That would not do that. That would not. I could not do that in general, because if I start in a superposition, let's say, to give you an example of this, let me give you a canonical example of this. Say I use the state, I use sigma x, acting on the state 0 plus 1 is the same as 0 plus 1, right? But if I do sigma x acting on the state 0 plus I1, I get something which is unitarily equivalent to 0 minus I1. They're not the same state. So this relative phase between the state matters, especially if I start off in a superposition of these phi's and psi's. That's why I want the relative phase to be important.
Yeah, come back, but I mean, I just don't see why in unitary controllability I can't define the states phi 1, phi 2 through phi
Okay,
n
so if I do that,
with some particular phase. So it's just the definition of, because every state, I mean, unless I want to mod out the phase, I mean, every state has a phase convention associated with it.
that's right. But the thing is, if
I'm calling phi modulo the phase, then I have to put that phase
right, so I
in
could
there.
always do this. I could say phi, let's say phi 2 twiddle
Yeah.
is either I phi 2, phi
Yeah.
2.
Yeah, that's what I wanted.
I could do that.
Yeah,
But then I would have to do the same thing with the other state phi 3 twiddle.
absolutely, absolutely. So
But it
every
has to be the
state,
same phase. I cannot give a different phase to all the
Why
similar
not?
states.
because then then my W is exactly psi goes to phi tilde.
Because then if I start in a superposition, now let's consider this state, phi 2 plus phi 3,
Yeah.
right?
Mhm.
And I consider this state, and I consider the state with the twiddles.
Well, they're different states, obviously. Those are different states.
Yes, so these two are not the same state,
Fine.
right? Now if I absorb the phase in here, this state and this state will not be mapped to the same state. So that's why the phase is important. It's like the relative phase between these two state matters, and because I'm absorbing a different phase into each of them, it would make a difference.
But I don't understand why this is not equal to this. I mean, I'm just defining this thing to be this, so this is an equality.
Right.
And so it's going to, relative to that phase convention, do the right mapping.
Yes.
With the right phase.
You're right. You're right. I could do it that way, but then this will not be the fiducial basis, and in particular depend on the spectrum of the unitary.
That's right, okay, all right. So it's a question of if you have a particular phase convention
Yes.
that you want for psi and phi, that's
Yes.
sort of
So
canonical,
Yes.
then I better put in the phase.
Right. So typically these are some kind of canonical basis that I'm interested in, and I have a particular phase convention with respect to that. And that phase really depends on the spectrum of the unitary I want to implement.
Okay, got it. So with that caveat, I agree.
Thank you. Right. So this is what I want to do, and this is a much more complicated thing, but I'm going to state the tautology, which we tried to prove in another way, and just state that I have, if I have SU, if my reachable state is the same as the dynamic exponential map of the dynamical Lie algebra, this is equivalent to the statement that I have unitary control ability.
And I would say that the reachable set is equal to
Yes. Did I say that? I thought I said
well,
exponential.
there is, I mean, it's not exactly the same, right?
Okay.
I mean, we were talking about cases in which
Sorry. I'm trying to rush. Okay, this wrong. Right? And a subset of this is pure state control ability. Alright? Great. So now, are there any questions so far? Okay. So now I want to give you something different and something more, something which I find a little hard to believe myself. Yes.
So, I mean, that's like a theorem.
Yes.
how do you check that that's the case? How do you prove?
Yes, that's what I'm getting.
Okay.
So something which I find very, in a way, magical, but the question is, how do I show this? Well, we need to generate a basis for L, the dynamical Lie algebra. And well, how do we do that? Well, we do that, remember that what we want is the set of elements to be the dynamical Lie algebra, and by these braces I mean linear combination and commutators thereof. So in order to do that, and I'm going to call this thing the span of the set of all controls of all Hamiltonian terms. Right, so how do I do this? Well, in order to do that, I just follow a simple process, which is I just list them out, keep taking linear combination commutators, and see if I get a basis for a big enough Lie algebra or not. So let me just write that down, and then we'll just do a couple of examples. of this. So you start with step 0. You start with the set S, which is a basis for the dynamical Lie algebra, which is just a set of terms which are there in my, which I already have in the Hamiltonian, right? Then I iterate. So while not done, and you could think of done as a flag, which is saying whether I've finished the end or not. Do the following. What you do is calculate Lie brackets or commutators, if you will. Right, so you take them and you calculate the Lie bracket commutators of these guys. Right? Now, of course, I'm sort of sweeping this under the rug because you don't want to repeat this. I'm not explaining that you don't do the same thing again. And then you do this and then add linearly independent terms, or add new linearly independent operators to S. So what this means is S is just S union whatever new stuff you find. Right? And if the dimension of S is n squared minus 1, you're done. Or the other possibility, else if elements repeat, and what I mean by that is the algebra closes on itself, you're done, right? So either the algebra closes on itself or you reach the dimension of the Lie algebra that you want to do, SUN, then you're done. And once you're done, you have the full, so either you have got the full Lie algebra or the algebra closed on itself prematurely, right? If this is true, you're not controllable. This is not controllable. And if this is true, then you are controllable, right? So this is how you generate the Lie algebra, right? You go with me? So I'm going to quickly do a couple of examples, and we'll stop there. So the first example that I have is our canonical example of a spin 1/2 system in a magnetic field. So my Hamiltonian is just say gamma Vx sigma x plus, and these are functions of time. So in principle, I can turn these on and off, right? So step 0, I get sigma x and sigma y, right? Then I take the commutator. Step 1, I get sigma x, sigma y, and this is my set S. And I see that this has dimension of S is 3, which is 2 squared minus 1. So I'm controllable. Alternatively, if I were to go further, you would see that if I do this, this algebra closes on itself. So in both cases, I'm done. So this is, so e to the L is SU2, and we are unitary controllable. Happy face. Now the example which we talked about where you're not controllable, let's take one. So now, let's say my Hamiltonian, it consists of 2 spins and I have some magnetic field along the x direction. which acts symmetrically on each of them. So this acts on the right spin. Forgive me about the factors of 2. Right? Plus I have an interaction between them, plus j, which say is time independent. Right? Now, forget about the factors of 2. At step 0, what do we have? Well, step 0, we have this term, and this term. So I'm going to write that as sigma z, identity times sigma x, and sigma x. So this is what I have. Right? Now let's look at what the commutators in the next step are. So the next step, I take the commutator and I get the terms. I'm going to write the new terms. I did not write the whole thing. So the new terms are I sigma z sigma y plus I sigma y sigma z. Right? Step 2, no new terms. So the algebra has closed. So what does this tell us? It tells us that the Lie algebra has a dimension of 3. The 1, 2, and 3. So in this case, the dimension of the dynamical Lie algebra, of L is 3. However, the dimension, this is a 4-level quantum system of SU is 15. So what this tells us is I am not pure state controllable. I am also not unitary controllable. In fact, my Lie algebra is spanned by these elements. These two and this one. So I have a Lie algebra of dimension 3, but to be fully controllable I need dimension 15, which I don't have. The Lie algebra closed on itself prematurely, so I'm not controllable. So it's the sad about that.
So what is the group?
Yes, thank you. So this group is actually isomorphic to SU2. So this has an isomorphism to and in order to see that, well, let me talk about the algebra because it's easier. I'm going to talk about the algebra elements. So there's an isomorphism to the algebra SU2, and I can see that by doing this. I sigma x times identity, map this to say sigma x with a bar or a quizzle. I over 2 sigma y sigma x plus and then finally the ZZ term. And if I do this mapping, these guys obey the same commutation relations as SU2.
First
and
one should be 2 terms, right?
What's that?
The first one should be 2 terms, sigma x. Sigma
Yes.
x I plus I.
Yes. Thank you. Now what I have is the same structure as an SU2 algorithm. Notice that if you talk in terms of subsystems, this is not really separable because I'm introducing 2 body terms here. So there is entanglement generation. I can make entangled states using this Hamiltonian. In fact, a lot of trapped ion experiments and even neutral atom experiments do it using Hamiltonian of this kind. But it's not fully controllable. draft your other question?
No, no. I was confused for a second about the eyes here versus the eyes there, but then I remembered the commutator of X and Y is the eyes there.
Yeah, I guess this is why Chris likes to put the eyes in the generator. Right? So this is an example of something where I do get a subgroup which is isomorphic to SU2, but it's not the full group. So I'm not fully controllable. But it's not, this is still useful because of these two body terms, I can do entanglement. In fact, something like this lets me generate gates like control Z and Goldman solve Z. But I can't do control not with this. Right? That's all I have. Thank you.